Last Thursday and Friday we talked about what organic chemistry was. What were some of the things that we do, like carbon-containing compounds that do not contain, or that are not contained within organic chemistry? What are some of the things that would be not contained in organic chemistry? There's 7 things. Two compounds and 5 ionic or polyatomic ions. So the oxides of carbon are not considered to be organic chemistry. So carbon dioxide, carbon monoxide. HCO3, negative, and CO3, 2 negatives. They contain those. They're not considered to be organic chemistry. Then we had FCN, CN, and OCN. So thiocyanate, thiocyanate, cyanide, and I'm not sure what the name of that guy is. Plus carbon dioxide, carbon monoxide. Everything else that's containing carbon is considered to be part of organic chemistry. We also defined an alkane. What was an alkane? Was a hydrocarbon containing only carbons and hydrogens and only has single bonds. Today we are going to look at a subcategory of alkanes, which are called cycloalkanes, and then we are going to look at both alkenes and alkynes. Alkenes containing double bonds and alkynes containing triple bonds. Again, we're only going up to 10 carbons in the parent chain. Based upon empirical evidence, i.e. Mass spectrometry and percent composition, we know that there are compounds that contain C4, twice as many hydrogens as carbons, but don't contain any double bonds. The double bonds are easy to test for. I'll show you how to do that here. So they contain twice as many hydrogens as carbons, and they don't contain double bonds. Well, the only explanation for that is instead of the N carbons in a propane, the N carbon, or the N hydrogens, I should say, disappear, and then you have a change. You have these guys forming a bond, so you end up with a ring. Same thing with cyclobutane, four bonds in a row, or 4 carbons in a ring. So an cyclo, either whether they're alkanes, alkenes, or alkynes, they are in a row, right? Or not in a row, in a ring. Again, we are basing this figure on empirical evidence. We don't take our theories and go, that has to fit. No, we have to fit our theories to what we see. And one of the ways that we do this is called percent composition. How much of this guy is carbon? How much is hydrogen? And since there are no double bonds, we just have to come up with this rule. Now, the basic thing is alkane. We're going to name them the same way we do alkanes, but we are just going to put the word cyclo in front of the system. So here we have 1, 2, 3, 4 carbons in a row, or in a ring, I should say. So this guy is called cyclo, or the parent compound for this is cyclobutane. That 4 carbon ring is cyclobutane. Now you notice how I numbered it. I numbered it starting at a branch, and I numbered it through my branches. This branch contains 1 carbon. This branch contains 1 carbon. So we have methyl branches twice. Call this 1,2-dimethyl cyclobutane. I number it again so the branches are off the lowest number. I don't start going 1, 2, 3. No, I go, so it's off the lowest carbon, just like we do with the normal one. This is, by the way, what is this an isomer of? Actually an isomer of hexene, because it has twice as many carbons as it does hydrogen. How many carbons in this one? 1, 2, 3, 4, 5, 6. So the molecular formula is going to start with C6. Now we have to count the number of hydrogens. There are 3 hydrogens off of that carbon, 3 hydrogens off of that carbon because it's an N. This has 3 carbon-carbon bonds. There's 1 more hydrogen coming off of that guy. Here we have 2 carbon-carbon bonds, so there are 2 more hydrogens coming off there. Same thing here, 2 more hydrogens here. And then this guy has 1 more hydrogen. Because how many bonds can carbon form? 4. There's no double bonds indicated in there, so I've got 3, 6, 7, 9, 11, 12. C6H12. Which is not the same formula unit as we talked about with just alkanes. If I had 6 carbons, I would have twice as many plus 2. Here I just have twice as many. This guy has the same chemical formula, or the molecular formula. This guy here, though, is called, I don't care which direction you go, you're going to end up with 1,3-dimethyl, 2 branches containing 1 carbon off the first and third carbons. And then we have our cyclobutane, because we have the ring formed with that. That's the smallest number of carbons you can have that forms a ring. Yeah, 3. Smallest cyclo is 3. So, looking at this guy here. Here we have a condensed structural diagram, kind of ugly, but we have no branches, so it makes my life a little easier. Got 1, 2, 3, 4, 5, 6. No branches. Cyclohexane. Molecular formula is fairly easy on this one. C6H12, and we can see all of them with that condensed structural diagram. This one here, we have 5 in the ring, so this is cyclopentane. And the way I have it numbered right now, off the first carbon, we have an ethyl branch, i.e., it contains 2 carbons. And off of the third carbon, we have a methyl branch. Now, I would also accept 3 ethyl, 1 methyl cyclopentane, although I think the one in red is more proper because now the number is in order too. But it is technically correct. Branches are off the lowest carbons. So I had to number in a counterclockwise direction in green. I could not have numbered 1, 2, 3, 4. Because I would then, again, that 4 would be too big. So number, so everything stays the smallest. Going backwards, we have the parent. Jamie, how many in the ring for cyclohexane? 6. I tend to, oh boy, that's just terrible. I tend to use line structural diagrams when I'm doing rings because less problems. We have doesn't matter where I put it, I have a methyl branch off of a first carbon. And because I have a habit of going clockwise, we also have a methyl branch off the third carbon. If yours can be rotated to look like mine, it is correct. We could have gone counterclockwise, we could have started somewhere different, etc. So when you have those rings, you've got to remember the prefix indicate the ring is there, is the cyclo. All right. So that's finishing up our alkanes. We talked about just a alphatic compound, the alkanes. Alphatic means straight chain or not containing benzene, which we'll talk about in a day or two. There is empirical evidence that there are compounds that contain double bonds and have twice as many hydrogens as carbons. There is also ones that contain triple bonds, which would have twice as many -2 and a triple bond. Okay. So these are both alkenes. As I said, it's not a spoken language because you really have to emphasize the ANE or the ENE or the YNE. These are, notice what's the only difference in the name. The suffix ENE. Now these are called unsaturated hydrocarbons because we can break bonds. This bond can break, put another hydrogen, and put another hydrogen there to form a saturated hydrocarbon. Now, this idea of breaking those bonds, we are going to talk about 7 different types of reactions that we have to remember. This is an example we could call hydrogenation, or we can actually call this, and the larger category, instead of hydrogenation, is an addition reaction. So there are many reactions that follow addition. Hydrogenation is the addition of hydrogen. So you have the unsaturated hydrocarbon here. We add it, we put it in the presence of some extra hydrogens. One of these bonds breaks, has to do with the sigma and the pi bond. Although, again, not what we're going to be talking about, but they are slightly different bonds, so one is easier to break than the other. And we end up with a saturated hydrocarbon. Same thing here. You have a triple bond, and you can form a saturated by hydrogenating, adding extra hydrogens to this. So an addition reaction is basically unsaturated plus a small molecule to give saturated or more saturated, depending upon if there might be more bonds to break. But essentially, you're breaking a double or a triple bond in an addition reaction. Got it all prettified there, Alexis? And this is just me. Now, as I said, they're the larger category. We can get a saturated hydrocarbon, as we just talked about, a chloroalkane, which we'll talk about later, or an alcohol. But none of those have the same number of double or triple bonds that they had previous. We've broken at least one, possibly all, of the double or triple bonds to form an unsaturated molecule or a less saturated molecule. So we'll spend a little more time on on addition reactions later. Do you need to remember hydrogenation? No, not really. Not yet. Once you get to university, you definitely will. And you take organic chem. But again, it's an unsaturated molecule becoming saturated by the addition of small molecules. In this case, it was H2, HBr, HOH. Those are other small molecules that we would add to the system. Okay, so alkenes are our unsaturated that only contain double bonds and single bonds. Double carbon-carbon bonds and single carbon-carbon bonds. Because we only have single carbon-hydrogen bonds. If you have one double carbon-carbon bond, you will have twice as many hydrogens as you will carbon. Just like we had with cycloalkanes. Okay, so either you have a ring structure, if you have twice as many carbons or twice as many hydrogens as carbons, or you contain one double bond. If you have more than one double bond, you basically have two less hydrogens for every extra double bond you take off, or you have. So if I have three double bonds, I'm going to have two hydrogens off on a normal twice as many plus two, compared to the twice as many plus two that we usually have with single bonds. If I have three double bonds, I've got six less hydrogens. Alkenes, so examples here, C4H8, this is our CnH2n, twice as many. This guy has got two double bonds, so he's CnH2n minus 2. When we start to talk about alkynes, we're talking about a triple bond. So if it contains one triple bond, twice as many hydrogens minus 2 as you had of the carbons. And again, you can probably see why on this slide here. To form this guy here, you had to break a carbon-hydrogen bond twice to form the top one, and a carbon-hydrogen bond twice to form the bottom one. So you've taken away 4 hydrogens from an alkane, or there's 4 less hydrogens than an alkane. Now this one here is a very, very unstable one, I would assume, but because I have 2 triple bonds, I have 6 less. 8 less than I would normally have. Because I have, again, to form this triple bond, I remove 4 hydrogens from a saturated, and I remove 4 for that one. So when we talk about the formula unit, if it's CnH2n and it contains multiple bonds, it's going to be either, in this case, it's going to be an alkyne, but it can also be an alkene with a ring structure. The naming of these is built upon the naming of the alkanes. We name very similarly. Okay, so what's the prefix, Rory, for one carbon? Sorry? Matt. Started with the right letter. Sean, what's it for 2? Kyle, for 3. Pro, for 4. Bute. Alexis, 5. 10. 6. X, 7. Hep. Chloe, 8. Oct, 9. Non, and 10 is death. Okay, we're going to use those prefixes. We're just going to change the suffix, and we're going to change a little bit about that suffix. So we're still going to find and name the longest chain, but here we have to make sure that the longest chain contains the multiple bond. Okay? We're going to number, so the multiple bond is off the lowest numbered carbon. When we did alkanes, we were worried about the branches, but multiple bonds trump branches. That's the most important part. We can deal with the branches later on, but we want to know where that multiple bond is, and we want to put it in our lowest. So for this guy here, we have 4 carbons. This is going to be called butene. But there are 2 possible forms of butene. There's one I've got drawn there, and I've got one more. So I have to indicate that this is called but-2-ene. 2-ene means that I messed that up. Because I saw a double bond when I should have saw a triple bond. It's ine, triple bond, ine. It has a triple bond, and this is telling me the carbon that it comes off of. 2 comes off the second one. I can also do but-1. That would be but-1 ine coming off the first carbon. And again, I do tend to work from left to right, although we don't always do that on exam. This down here is again but because it has 4 in it. They're all double bonds, so it's going to end in E-N-E. But we have 2 double bonds, so what do you think I'm going to put in front of the E-N-E? What's the prefix? What's a prefix that indicates 2? Okay. But something di-ene. But now we have to say which ones they're coming off of. But-1,2-diene. I said this is not a really good spoken language. Now, if we throw branches into the works, well, we do just like we did before. Our our parent chain. Okay, so that's a 9, non-ene. Okay, we again have 2 double bonds, so diene, and 3,4 non-3,4-diene. Off the third carbon, I have a double bond. Off the fourth carbon, I have a double bond. Question? Now we go ahead and name the branches as we did. Off the third carbon, we have an ethyl branch. Off the sixth carbon, we have a methyl branch. In this case, numbering from left to right gave me the lowest numbers anyways. But if I had put a branch right here, I would still name from that way because the double bonds trump are more important than my branches. So I'm going to number my double bond, so my double bonds are less, the lowest numbers possible. I don't want to see two ethyl, two ethyl, pent, 4 ene. I would number it the other way around because I want to see the ene off the second, not the fourth. So in this one here, I'm going to number this direction. Why? Because my double bond is there. Go ahead and name that one. I'll give you a minute. All right, so this one here is 7 long. Prefix is hept. Suffix is ene because of the double bond. And this is off the first carbon. So we have hept 1 ene as the parent chain. We have 3 ethyl, indicate that branch, and 2 methyl. Now, question, what is the formula for this? Well, we have 1 double bond. We have 10 hydrocarbons, 7, 8, 9, 10. Since we only have 1 double bond, we should also have 20 hydrogens. Where do I get my 20 hydrogens from? 1 from there. 1, 2, 3 from there. Because it's an N. I've already got 4 carbon-carbon bonds there. There's no hydrogens at that one. There is one hydrogen there, two there, 1, 2, 3 there. Two carbon-carbon bonds, two more hydrogens. Same thing here, and then finally at the end we have 3. So 3, 5, 7, 9, 12, 13, 14, 15. Did I mess up on? Missed one somewhere. 3, 5, 7, 9, 12, 14, 15. Oh, yeah, that's where I missed it. There's actually 2 there. Because there's 2 carbon-carbon bonds, the other 2 have to be filled with hydrogen. So we do have C10H20. This one here is 1, 2, 3, 4, 5, 6 long. So hex, Y-N-E, hexine. My triple carbon-carbon bond comes off the second. And then we have 4, 5 dimethyl for our to name our branches. Now I have okay, we'll do that after this one. So pentene. Pent, 5 carbons. Off the first carbon, I have a double bond. So that means I need one more there and another one there. And off the fourth carbon, I have one methyl branch. So but-1-ene would look like this. Now there is a mistake with, there's a mistake with my name. Okay, I just have dimethyl but-1-ene. Problem is, there's two things that I can do here. So I made a mistake with this. So I'm going to put in here 2,3-dimethyl but-1-ene. So I have one carbon branch off the second, one carbon branch off the third. Need another hydrogen there. Need 2 more hydrogens there. Because again, I always have to have 4 bonds off each carbon. Please draw 2-methyl hex 3-ine. And then tell me what's wrong with the name. Or no, it's hex, never mind. There's 5. 1, 2, 3, 4, 5, 6. Off the third one. There's your 2-methyl hex 3-ine. I do the parent chain first, put the branches on, and then I put lines to indicate each hydrogen. The next question is, why is it just called propene? Why is it not called prop-1ene? The reason is there's only one place to put the double bond in this case, right? If I write it the other way, the purple one is still prop-1ene, not prop-2ene, because I just number that going that direction. So it's still prop-1ene, so there's no option in that case. That would be similar as if I did this guy here is just called methyl propane, because there's only one place that carbon can come off. Because if it comes off the end, guys, now it's butane. Quickly run over cyclo. So there is evidence of ring structures and double bonds at the same time. We're basically going to do the same thing. We're going to name the ring and then number our branches as necessary. Here we've got, now the thing that you have to remember with this is you're going to number across the double bond. Okay? We don't go 1, 2 this way. We have to go across the double bond. So we have our 6 here. We are going to call this cyclo X 1-ene. Cyclo because it's in a ring. The 1-ene because our double bond is coming off of the first one. Now, in truth, with that guy, I could get away with just calling this cyclo Xene. Why? Because there's only one double bond, and I'm always going to start numbering at that double bond. If there was 2, I would definitely have to put my numbers in. And then I have 4 ethyl, 3 methyl. Okay? This is probably the one that you're going to see. If there's multiple double bonds, then you would have to definitely put numbers in. This one here, 1, 2, 3, 4, 5. So this is 5 ethyl, 3 methyl, cyclo Xene. Now, this one here probably is going to be numbered that way. Numbering it that way could also work because it follows all of our rules. The only reason why I'm going to number it in purple for the most part is alphabetically and numerically will it stay the same. It's in purple. This is 3 ethyl, 6 methyl. Oh, wait. Cyclo Xene. Although, if someone on written response, gave me what I wrote in red, fine, I don't have a problem with it. It is, you're numbering through the double bond, The numbers are still 3 and 6. The reason I would say the purple would be the proper one is because the numbers in the alphabetical match up. We go 3, 6 instead of 6, 2. Cyclopentane, little house, terrible at it. Dimethylpentine, so pentine, I need a triple bond. 1, 2, 3, 4. So off of this guy, I'm going to have a leg, and I'm going to have a leg off of that guy. Again, does it have to look exactly like that? No. I could have numbered going counterclockwise and get the same thing. Now, I have not printed that assignment, so I'm going to give you time to work on the other assignment while I go get it. Or have I given you the second assignment? Hey, yay, I gave you the second assignment. You can use structural diagram and take structural plan. And I'm going to give you this. There's no double bond in this.
tell me where that double bond comes from. Numbers. One, three, four. I want that one. Are but those are your five.
Where there are only 4 cyclic isomers for 5 So 9 total. And that's everything for tomorrow. Yeah. Post A plus A. Minus A. Like post A. Okay, so I guess it's just adding. Yeah. So just plug it into the formula and I should be able to figure it out. All right, thank you, Mr. Roby. I will be putting on the notes. The contributor one. Alright, so obviously will be a video sent out, the video link sent out to the class, like I do every day. I will, will there be a recorded one if you want one? That's what I'm sending out. I'll send out the link to the class. Perfect, thank you. Yeah, basically, yeah, not very, very exciting. That's all right.
Mrs. Terry Wayland, if you're available, can you stop by the office, please? Mr. Knack, can you please call into the office?